Hello. In this video we're looking at one of the most important analysis techniques that we use when we have bivariate data. And by bivariate data I mean where we've taken more than one measurement for each observation. And the analysis we're going to be using is correlation analysis. So let's start by looking at an example of some data where we might want to know if there is or isn't a correlation. These are some data that were published by Rylance et al. In 2015 in PLOS One, and what the authors of this study were looking at was the relationship between smoke particulates in the air and immune responses in households in Malawi. So each of these data points is an individual household in Malawi. On the x-axis we have a measurement of the amount of carbon particulates in the air that are being caused by people cooking on open fires in their houses. And on the y-axis we have something called the Oxidative Burst Activity Index. That's a measure of how strong a certain component of the immune response is in the people living in those houses. So you can look at this scatter plot that I've drawn here and you can see that there is maybe some kind of relationship there. Certainly for the high particulate burden people, we don't have any of the really high oxidative burst data. But the overall picture is quite difficult to understand. I don't think you can look at that and just say, yes, I'm sure there's a correlation there, or no, I'm pretty sure there's no relationship there between the amount of particulates in the air and this particular aspect of the immune response. We need to be able to quantify how strong the relationship is between the two variables, and then we need to be able to ask how likely we would be to see that kind of relationship were there no actual relationship in real life. So first of all we need to quantify how strong the relationship between oxidative burst activity and the particulate burden is. What I've done here is I've drawn in the mean values for our two variables. So the mean for the x variable is the mean particulate burden, the mean for the y variable is the mean for the oxidative burst. And what I'd like to think about is what results we would get if we subtract the mean of the x variable from each x value and the mean of the y variable from each y variable, and then for each observation we multiply those together. Those are the means. And so for each observation we would take the x value and subtract the mean and then multiply that by the y value minus the y mean. So let's think about what results we would get if we were to do that. And we'll start with this data point here. This data point has both an x value and a y value that are greater than the mean. So both the x value minus the x mean and the y value minus the y mean will be positive. So if we multiply that together, that will give us a positive result because we're multiplying two positive numbers together. And that will be the same for any number, for any data point in this quadrant of the graph, where the quadrant is defined by those two means. So any data point with both an x and a y value greater than the mean will give you a positive value when you subtract the mean from each variable and multiply them together. So all of the ones in that part of the graph would give us a positive result. Let's look at this part of the graph now. This data point has an x value which is greater than the x mean, but a y value which is less than the y mean. So the x value minus the x mean is positive, but the y value minus the y mean is negative. And if you multiply those together, that will give you a negative product, because the product of a negative and a positive number is a negative number. So for all the values in this quadrant of the graph, we're going to get a negative value when we multiply these two things together. Moving on to this part of the graph, well, this data point here has an x value which is less than the x mean and a y value which is less than the y mean. So both of those will give a negative result if you subtract the mean from them, and then if you multiply those two values together, you're going to get a positive number, because a negative value times a negative value is of course a positive number. So all the values in this bottom left quadrant of the graph are going to give you a positive product when you multiply those two quantities together. And then moving on to the last part of the graph up here, this data point here has a y value which is greater than the y mean, but an x value which is less than the x mean. So if you subtract the means from both variables for this data point and multiply them together, you're going to get a negative value. And again, that's going to be the case for all the values in that quadrant of the graph. So if we have, for example, a data set with a strong positive correlation, like this, and we subtract the means from both variables for each data point and multiply them together, almost all of our values in this case are going to be positive, because almost all of the data points are either in that top right or the bottom left quadrant of the graph. So calculating these values and adding them together is going to tell us something about the nature of that correlation, and we would expect to get quite a large positive value if we were to do that. Similarly, if we have a strong negative correlation and we calculate the sum of these products, then almost all of the values we get are going to be negative, because almost all of the data points are in that top left or bottom right hand quadrant of the graph this time. And so if we were to do that with a data set with a strong negative correlation, we would expect the sum of those products to be a fairly large negative value. So let's do that for our data set here. We're going to calculate the sum of x minus x bar times y minus y bar, which is otherwise known as the sum of products. And that gives us a value of minus 133. So we've got a fairly large negative number describing our correlation. Now, is that much use to us? Well, it's not really much use at the moment. It's telling us something about what's going on in our data set, but it isn't very easy to compare this value with values from any other data set. And one of the reasons for that is that this value is going to get bigger if we add more data. So as you add more data into your data set, assuming the relationship stays the same, then this value is going to change. So we need to do something to correct for the fact that this value is going to be dependent on the sample size. And what we can do is we can divide our sum of products by the degrees of freedom. And the degrees of freedom is n minus 1. You might say we've calculated two means. Well, we have, but we've calculated one mean for each variable. So the degrees of freedom are n minus 1. So we calculate the sum of products divided by the degrees of freedom. And for the case of our data, that's minus 133.19 over 28, which is minus 4.757. And this gives us a value that's called the covariance. And the covariance is a useful value in some circumstances in statistics, but it's still not particularly useful for our purposes because it still depends on the units that we've actually measured our data in. So if we were measuring human height in nanometers, for example, all our values would be very, very large, and that would give us a very, very large value for the covariance. If we decided instead to measure human height in kilometers, all our values would be very, very, very small, and that would give us a very small value for the covariance. So this value, the covariance, is scale dependent. It depends on the size of the numbers that you're putting into it, and we want to correct for that as well. And we can do that, we can standardize the covariance, and we do that by calculating this quantity. So on the left we've got the covariance that we just calculated, and then we're going to divide our calculated value for the covariance by the standard deviation of x multiplied by the standard deviation of y. And in the case of our data set, that's going to be the covariance that we calculated before divided by the standard deviation for the particulates measure multiplied by the standard deviation for the oxidative burst data, and that, if you take it, gives us an overall value of minus 0.395. So we've still got a negative value. It's a negative correlation that we're seeing, but this value is now minus 0.395. You probably noticed that I've started writing R equals on this slide, and that's because what we've calculated here is our final result when we're trying to do a correlation analysis. This is the grandiosely named Pearson's product moment correlation coefficient. No one ever calls it that. Everyone either calls it the correlation coefficient or more usually just R. So we've calculated R for our data set, and The correlation coefficient is a very useful statistic. For any bivariate data set, you can calculate the correlation coefficient. If the correlation coefficient is close to 0, then you're going to have a very weak or no correlation. If it's a positive number, you've got a positive correlation, and the closer to one it gets, the stronger that positive correlation. If you've got a negative value, it's a negative correlation, so high values of one variable are associated with low values of the other variable, and the closer to -1 it is, the stronger that negative correlation. It will never be more than 1 or less than -1. Just to show you some examples of data with strong and not so strong correlations. Here are a couple of data sets with a strong positive correlation on the left and a not so strong positive correlation on the right. Down at the bottom, I've written in the actual correlation coefficient. So this is a really strong correlation. R is 0.98. On the right, we've got a weaker positive correlation with R is 0.6. If you're an ecologist, you probably wouldn't call that a weak positive correlation. If you're a physicist, you'd probably give up science if you got something like that. But as an ecologist, if you got a result like that, you'd be pretty pleased, and you wouldn't call that a weak positive correlation. You'd call it a moderate or even a strong positive correlation. If you're an ecologist and you get a result like the one on the left, the first thing you do is ask, what have I done wrong in my calculations? Here are a couple of negative correlations. Once again, we've got a very strong negative correlation on the left with a Pearson's R of -0.98. And on the right, once again, if you're a physicist, you'd call that a weak negative correlation with an R value of -0.68. And again, if you're an ecologist, you'd call that a moderate or a strong negative correlation. And then finally, here's an example of some data that have effectively got no correlation or a very, very weak correlation. And the R value here is 0.11. So we can calculate our R value for our data. And in the case of our immune data from Malawi, that's telling us that there is a negative correlation between particulate burden and oxidative burst. And it's telling us that it's a weak to moderate negative correlation. What we need to know, though, is whether or not this correlation is statistically significant. In other words, how confident can we be that we wouldn't see a result like this if there were actually no correlation at all in the actual population we were measuring? What's the probability that we just by chance happen to get a few data points with a high particulate burden and a low oxidative burst index, and then a few data points with a low particulate burden and a high oxidative burst activity index, and then just got this pattern by sampling error, by random chance? How likely would we be to see an R value of -0.395 if in fact the actual population value was 0? Well, it turns out that we can actually calculate a t value based on our correlation coefficient. So if we multiply the correlation coefficient by the square root of the sample size -2 and then divide that by the square root of 1 minus the correlation coefficient squared, that gives us a value that we would expect to be distributed on a t distribution with n-2 degrees of freedom. So our t statistic that we've calculated is 2.232. And we can then use that to do a statistical test. We can do a t-test with that. Our test statistic is 2.232. We've got 27 degrees of freedom because it's n-2 degrees of freedom. And we can just ask R, what's the probability of getting a value as big as 2.232 or bigger if the null hypothesis were true on a t distribution with 27 degrees of freedom? And the answer is the probability is 0.034. So 0.034 is less than 0.05. So there's only a small probability that we would have seen a relationship like this if there were in fact no relationship in the population we're sampling from. And so we would say that our correlation coefficient is significantly different from 0 at the p equals 0.05 level. One thing to mention here is that you shouldn't get confused between the p-value for a correlation and the correlation coefficient itself. If you have a very large data set, it's possible to have a very weak correlation with an R value that's close to 0 that is nonetheless statistically significant. And if you have a small sample size, you can have quite a strong correlation coefficient and have it not be statistically significant if the sample size is small enough. So don't get confused between the p-value and the r-value. They're telling you two different things. Okay, last thing to think about is, well, we don't always want to calculate correlations by hand, fun though it may be. Sometimes we want to get a machine to do it. This is how you would calculate a correlation coefficient in R. You simply use the core.test function, and then you give it as arguments the two values that you want to work out the correlation for. In this case, the amount of carbon, particulates, and the oxidative burst activity. So we fed this into the core.test function, and it's given us Pearson's product moment correlation. And you can see that the values that are coming out are pretty much the same, give or take a little bit of rounding error, as the values that we've just calculated. So T is minus 2.23, 27 degrees of freedom, p-value 0.03. It then gives us, rather usefully, a 95% confidence interval on our estimate of R. So we can now say that we can now give confidence intervals on our estimate of the correlation, and we can say what we would expect it to be were we to repeatedly sample 95% of the time. And then finally, it gives us that correlation coefficient again, minus 0.396 in this case. Thank you.